In our section today, last section for Chapter 9, we're looking at testing, doing a hypothesis test for a difference in proportions is what we're doing here. Is there a difference? So it's like maybe we're you can remember, proportions was categorical data. So maybe we're comparing males and females, or maybe adults and teenagers. We have two different types of data that's categorical, and we get a percent for each one. And we're going to say, hey, is there a difference? Is there a difference between, like, if I wanted to do one, and I did this with my honor stats class in the fall, is on AFT I sent out a survey to all the math teachers and asked them to give it to their AFT classes and it was an anonymous survey. So they did not have to put their name. I had to set up with a Google form. It did not record their student ID stuff. And it basically asked the question is, one, do you use AI to answer your homework problems? Do you, use a friend? Does a friend tell you the answers to your homework problems? I'm trying, because again, I had this feeling, I had this thought, this hypothesis that I would say over 60% of the students at this school cheat on homework using either AI or getting the answers from their friends. I think it's over 60% is what I really think it is. And so I mean, it wasn't a simple random sample, but they said I had like 9 classes respond to it. So I got over like 300, sets of information from it, which gave me a good sample. Okay, it gave me a really good sample. And I could break it down by grade level, 9th, 10th, 11th, 12th graders, and so forth. And that way I could test the hypothesis, is it more than 60%? And that's where I think it is. It is reasonable to claim that it is more than 60%. And if I wasn't sure, then I'd say, okay, it's going to be 50%. Because if I wasn't sure if it was, what it was, because I didn't have a sample done prior. Sorry, I saw a kid in the hallway, so I had to just peek using this for arts class. And so now it's like, I could do with that same survey saying, is there a difference in the proportion of students that cheat on homework assignments between 9th graders and 12th graders, or 12th graders and 11th graders? Is there a difference? And so that's what this topic today is going to do, is when we're comparing two proportions for categories, hey, is there a difference between it? And then say do more seniors cheat than juniors? Or, hey, maybe it's more of a younger high school student thing. Maybe there's a greater percentage of the freshmen that cheat compared to seniors. And that's when we can start when we look at, is there a difference? Is it more freshmen? Is that greater than the seniors for that aspect? So that's what today's topic is when you're trying to find the difference between two things, two proportions, and testing that claim. When we get back from spring break, we will do this again with means, and that's where we get to actually do the more fun activities, because funner is not a word. Is we get to do I like fun activities where I'm gonna bring in some chocolate chip cookies, the Chips Ahoys and stuff. I got a couple heads turned, and we're gonna see, is there a difference in the mean number of chocolate chips in a Chips Ahoy cookie, the name brand Chips Ahoy? Is there a difference between the mean number of chips in a chocolate chip cookie for Chips Ahoy compared to the off-brand? Okay, like Kroger's off-brand, or a Walmart off-brand of a chocolate chip cookie. And then we're going to say, is there a difference? Because we would think about it, well, most chocolate chip cookies from either of those things, not the big giant ones like the Mrs. Fields and some of those big ones, but most of those chocolate chip cookies that are the same size, like the Chips Ahoys and the off-brands, should have about the same, is what we would think. There shouldn't be that big of a difference. And so I'm going to bring in the cookies, we'll tear them up and count, and we're going to figure out, okay, is there a difference between those two things? And we're going to do that with beans. Proportions is a little bit harder to do, but like activities like that, hands-on, but we're going to do that. So, I'll make sure I let you know to bring extra drinks, bring your milk if you want to dunk some cookies in there and have milk and cookies and stuff on there when we do it. So as we look at our significance test, as we want to find the difference between the two populations in our hypotheses, an observed difference between two sample proportions it can reflect an actual difference in the parameters,
or it may just be due to chance variation in the random sampling or random assignment. Significant tests help us decide whether the explanation makes more sense. The null hypothesis has a general form of P1 is equal to P2. That's what our null hypothesis is going to be, that there is basically no difference. The proportion, it looked like the Chips Ahoy cookie. The proportion of chocolate chips in a Chips Ahoy cookie is equal to the proportion of chocolate chips in a off-brand chocolate chip cookie, is what we're saying. There's no difference. It's actually equal, is what we're looking here. For now, we're going to restrict ourselves to the situations with the hypothesis difference is technically 0. So that means our statements for our null hypothesis, give me a second, my pen turned off. So our null hypothesis, our H naught, our H sub 0, we're going to have it be P1 minus P2 is equal to 0. That the difference is actually 0. And again, that's the same thing as what I have up here in blue. That's the same thing, because if we start off with P1 equal to P2, and I subtract P2 over to the other side, well, don't we just get P1 minus P2 is equal to 0? And so when we write our null hypotheses, we're going to be using that as our setup there, that the difference is 0. We're expecting there not to be a difference, is what we're doing. Our alternative hypotheses, again, that we expect is that P1 is less than P2, or P1 is greater than P2, or they're not equal to each other. And again, you can always, and I'm not going to do this because it's going to junk up the screen, but we can always go through, and I'll do it on the first one, is bring the P2 over, like I did before. And we can say that, hey, the difference between P1 and P2 is less than 0, meaning that there's a negative difference. All right, if it's a negative difference, then what does that mean about P2? It means P2 is a bigger number. That proportion is bigger. If I'm subtracting those two things in the order of P1 minus P2, and I'm getting an answer that's less than 0, which means it's negative, that means that P2 has to be a greater proportion. It's got to be a greater percentage. Okay? And so, again, you can do that for the other two values there too. Here, when I do it, I would say P1 minus P2 is greater than 0. So that means that the difference is positive, which means P1 is bigger, is what that indicates. And then the last one, it would just be that P1 minus P2 is not 0. So it's something. I don't care if it's bigger or smaller, it's just not 0. It's not positive, it's not negative, it's not less than or greater than, it's just not 0. The difference is not 0. So, all right. So let's get in here, and we're just going to kind of write the null hypotheses in here. It says, are teenagers going deaf? In a study of 3,000 randomly selected teenagers in 1988 to 1994, almost the amount of time I was in college, 15% showed some hearing loss. In a similar study, 1,800 teenagers in the year 2000, in 2005-2006, 19.5% showed some hearing loss. Does these data give convincing evidence that the proportion of teens with hearing loss has increased? So has increased. So with that in mind, as I look at I'm going to let P1 is going to equal the teen, well, we're going to define it down here. P1 is going to be equal to the proportion of teens with hearing loss in 1988 to 1994. And then P2 is going to be the proportion of teens with hearing loss in the years 2005 to 2006. Now, when we do on an AP question, when we do a free response, we have to define what P1 and P2 are. Because again, we're using symbols in the null and alternative hypothesis. So we got to explain to the reader what those symbols represent. Now, if you want to use, let's say we're using teens for both of these cases, so it's hard to use the letter T as a subscript. But sometimes we'll have these problems with like men and women. So if you want to use P sub M and P sub D or sub W, then you would just need to say, okay, what does P sub M mean? It's the proportion of men. And then P sub W is the proportion of women, is what it represents to. So now we're going to write our hypotheses. Our null hypothesis is that basically P sub 1 is equal to P sub 2. Again, or we write it as P1 minus P2 equals 0. You can write either way on the AP exam. Either one of those two is fine. Our alternative hypothesis, they're saying that it has increased. So that means that P2 is greater than P1. So P1 is less than P2. That's what that's saying. By saying has it increased over time, we're saying that the P2 is actually greater than the P1. Is what we're saying there. So that would mean that I would have P1 minus P2 less than 0, which means the difference is going to be negative because P2 is technically actually bigger. So that's how we would write our null and alternative hypothesis for the difference between two things. Again, they will tell you how you need to do the subtraction.
We need the HEMA Club and the Art Studio, please.
Now, pooled samples for proportions. If the null hypothesis, P1 minus P2, is true, the two parameters are the same. We call their common value just P. But we know we need to estimate, we need a way to estimate P, so it makes sense to combine the data from the two samples. This pooled, basically, or combination or pooled sample proportion is a new standard deviation formula. And I'm going to write it down. So it is basically, as symbolically, it is P hat, PC hat, P combined hat. PC hat. Now, what does that formula look like when I do this pooling? Well, first off, to find out what PC hat is, we gotta take the we gotta combine the number of successes in both samples, and we got to divide that by the combined total, the combined total of the number of samples. So that would be like saying, again, we know successes is typically represented by the letter X. So this is basically taking X sub 1 plus X sub 2, and on the bottom, adding up the total sample of 1 plus the total sample of 2. And that's how we find our P hat, our PC hat. We would take the total number of successes, add it together by the total number of successes divided by the total sample that we have. All right, and so we don't have to worry about getting common denominators, it's just flat out adding. If I had 8 successes and 9 successes, then it's 17. And the total successes on the bottom, what's my total aim? It's just adding the two ends together. Now, what would the standard error look like, or the standard deviation look like? Again, if the 10% can be, remember, anytime we're doing standard deviation, the new standard deviation form, when we do the new standard deviation, remember, anytime we got to keep in mind the do we meet the 10% condition? If we met the 10% condition, our standard deviation of PC hat, that would be equal to the standard deviation of P1 hat minus P2 hat. So that would be the square root. And this is where the combining helps us. It's technically PC hat times 1 minus PC hat over N1 plus PC hat again times 1 minus PC hat over sample 2. And that's how I find the standard deviation to like use it in a normal probability, to use it in the normal CDF feature. Instead of using the P1 hat, the P2 hats, I'm actually going to combine them, and then I'm going to take that, I'm going to use that PC hat as my, and I use it twice in there with each sample size. That's what I have to do. Now, there's a little note with an orange star for UT fans. You only do this pooling for proportions. For the difference in proportions. That's the only time you do this pooling. When we do difference in means, we don't pool. We actually do that. We actually have each one represented separately. So the only time you pooling, that's why you got to look at when they're asking me to do a hypothesis test for the difference in means with proportion. I'm pooling the data together. I'm not actually for the standard deviation. I am not doing it P1 hat minus P2 hat. I am actually combining the two totals together, the X values and the N values to get a PC, hat is what we're going to do. We get to run through an example here in a minute as we get to do it. Whereas all the other time we were doing the difference between the stuff. So now this one we actually pull it and then we do it. All right, scooching over here. How would we set up our confidence or our hypothesis testing? Again, on our statement phase, we would test the hypothesis that the difference, so we change the phrasing at the beginning. We're going to test a hypothesis that the difference in the proportion of whatever's taking place, this one thing and the other proportion, is 0. And then we specify again the significance level. Again, you can use either one of these two hypotheses, for null hypothesis and alternative hypothesis. If you want to use the 0 in there, you can. If you just want to use the relationship between P1 and P2, you can. It's whichever one you want to use. And then, again, we got to make sure that we define. You got to define what your stuff is. What is P1 and P2? What are they in the context of the problem? We're going to use a 2-sample z-test for proportion. The data, and then again, we go through the process of is it random? And again, both samples, both groups have to be random. For normal, we're doing that both samples have to be greater than or equal to 10 for both parts. And then independence, both thing has to be, again, 10%.
FFA, please.
And then now compute the pooled sample proportion. So, again, we show this part here because we have the multiple choice questions on there. So this first part, compute, this would be this part right here is the PC hat. So we would want to do this on the piece of paper. What is X1 plus X2 over N1 plus N2? So we'd want to show that pool combined because, again, they're not going to do that. We got to show it, what that combined part is. Now, how do we get the test statistic? How do we get the z-stat so we can use a normal distribution? So how do we get the z-statistic? The z-stat is equal to P1 hat minus P2 hat minus 0, because remember our difference is 0, over, and this is where us doing that standard error stuff, doing that square root formula. So this is where we would go with the PC hat times 1 minus PC hat over N1 plus PC hat times 1 minus PC hat over N2. And again, once I get that Z statistic, again, I'm using the P1 hat and the P2 hat for the top part to find the difference, and then subtract it from the mean, which was 0. But on the standard deviation part on the bottom, we're using that PC hat percentage to do the bottom part of the standard deviation, the standard error. Now, when we go to calculate the p-value, we can use a normal CDF to go through that process, is what we can go through and do. Because again, once we convert it to a Z-stat, a Z statistic, that means we're now standardized, which means I can use the normal CDF, adjust my upper and lower bound accordingly, and then if we're using the less than and greater than, so we know that our Z statistic is either the upper or lower bound. If it's the not equal to, then we got to make sure that we don't multiply the H by 2. Remember the 2 times the normal CDF? If you got to do the not equal to symbol, you're going to be using it 2 times the normal CDF. Now that's one way you can do it. The other way that you can do it, remember that's the by hand way, especially when we see like multiple choice questions on the AP exam. That's the by hand way. We can use a two, sorry, my pen's not working. A 2-prop Z test. For the calculator, if we're doing the calculator version, we get to do a 2-prop Z test is what we get to do. And I'm going to split the screen and show you what that looks like. What do you have to type in? So if I go into stat over to tests, go down to 2-prop Z test, option, my crazy fingers. Option 6. And so here, that's where I would put stuff in there. Now, does anybody have an older version of a TI-84? You have a TI-83, Alex. Does it say like pooled on the bottom there? No. One of the calculators actually had the word pooled, like P-O-O-L-E-D. Like, hey, do you want to pull the stuff together? So, and I can't remember which version of the software actually had that. Most of you have your own newer version. Let me see if this other version has it. No, doesn't have it on here either. Okay. Okay, never mind. I don't think I imagined that. I remember seeing it at the bottom of the screen. Just don't remember when I've taught this course. So here you would just type in your X1 and your X2 and 2s and all that junk there. Choose your appropriate symbol of what's the difference between the two. Notice how it says is P1 less than P2 and blah, 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 blah. So it has it already set up for you. So you would just type the stuff in there, indicate on the AP exam, I'm using this test. What do you type it in for X1, X2, N2, N1s? And then, choose your inequality and then hit calculate. And so it does it real nice. And again, remember, that tells us the probability. It gives us the p-value. It also gives us our Z statistic when we do that. So we're going to use that here in a minute to do our problem instead of doing it by hand. Now, what do we conclude? Again, like always, we're going to compare our p-value to the alpha that they tell us. If the p-value is less than the alpha, we reject the null hypothesis. If the p-value is not less, which means greater than, then we fail to reject. We fail to reject the HO. Now, when we say that we reject the null hypothesis, that means we do have convincing evidence of the HA. To not support, we have convincing evidence to support the case, blah, 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 blah. And then if we say that we fail to reject it, we say we don't have convincing evidence of what's in the alternative hypothesis. So, again, that's just the general part. We got one problem, we get to practice, and then we get to turn you loose and let you do a whole bunch of problems in class and do things and ask me questions as you go. So, are teenagers going deaf? Going back to that study again. In an earlier study, 3,000 randomly selected teenagers in 1988 to 1994, 15% showed some hearing loss. Similar study, 1,800 from 05 to 06, 19.5% of them showed some hearing loss. Does these data give convincing evidence that the proportion of all teens with hearing loss has increased? So our state phase, we will test the hypotheses. There is no difference in the proportion of teenagers with hearing loss between the time frames of 1988 to 1994 and the time frame of 2005 to 06. Now, as we stated earlier, we said that P1 is the proportion of teens with hearing loss in 1988 to 1994, and P2 is the proportion of teens with hearing loss in 05, 06. Someone's knocking at my door. Let me get her. What's up, dear? Miss Ava. Your fault. All right. So we defined those. Now let's write our ho's and our ha's. I don't have a lot of space, so I'm going to go P1 is equal to P2. And then we're going to say that has it increased? And we said earlier, that P2 was bigger than P1 is what we said earlier up above in our problem. So P1 is less than P2. Has it increased? We're going to do a 2-sample z-test for proportion if conditions were met. So as we look at the thing, 3,000 randomly selected teens. So 3,000 randomly selected, blow that up, selected teens in 88.
We need the multicultural club
And-
and the virtual enterprise, please.
All right. So 3,000 randomly selected teens in 88 to 94, and 1,800 randomly selected teams. Randomly selected teens in 2005, 2006. All right, so we met the random clause. Normal, 3,000 times 15%, 0.15. That's equal to technically 450. That's greater than or equal to 10. 3,000 times 0.85, because that's the other part. That gives me 2,550. That's greater than or equal to 10. So we know the first group is normal. Now we go for the second group, is 1,800 times 0.195, 19.5%. That is equal to 351. That's greater than or equal to 10. Is 1,800 times 0.805. That is 1,449. That's greater than or equal to 10. So yes, we meet the normal condition for both. Independent. 10 times 3,000 is 30,000. 10 times 1,800, 18,000. We would say here, reasonable to assume. Reasonable to assume more than 30,000 teens in 1988 to 94 and more than 18,000 teens in 2005, 2006. All right. So now we got our conditions are met. We know we can do a 2-sample z-test. We do want to show what PC hat is. All right, that way we have it. So with that in mind, now we do have what NP is for both of those. We do have what the actual X value is. That happens to be like the 450, the 450 and the 351. So 450 plus 351 divided by 3,000 plus 1,800. Okay. And then that would give me 801 divided by 4,800. And that turns out to be a PC hat of about 0.167 is what that gives me for PC hat. Now, again, the reason I did that for when we go to set up our Z statistic as a formula, now we can use that 3-digit number for the PC hat. So as I do my Z stat, again, it's P1 minus P2. So that would be the 0.15 minus 0.195, the P1 minus P2, P1 hat minus P2 hat, and then minus 0. So that's the top. On the bottom, we got our big crazy standard deviation. It's going to be 0.167 times 0.833 over 3,000. Plus, again, same numerator, 0.167 times 0.833. And on the bottom here is 1,800. So there's our Z statistic. Remember, we write that down. We got to get in a habit of writing that down there because the multiple choice questions are going to have that kind of a setup of, hey, what's the correct Z statistic for this problem? So we got to get into practice. We don't always just want to go to the 2-prop Z test to find the answer because we need to know the setup for some of those basic questions. Now, as we simplify this for a Z statistic, we get on top negative 0.045, on the bottom 0.0, and then it's 111199. And that gives us an answer of approximately a negative 4.0468 as a Z statistic. So now if I want to go do a normal CDF, I can. I'm going to do the 2-prop Z test real quickly to get my information. So as I do a 2-prop Z test, my X1 is 450. My N1 is 3,000. My X2 is 351. My N2 is 1,800. We are choosing greater than. So we're saying that P1 is less than P2. Because again, on the calculator, it only gives you options for less than P2, not equal to P2, or greater than P2. So we want to choose where it says less than P2, or P2 is greater than the left side. So that's all the stuff I need to use to type in. So I'm going to split screen, get to my calculator, clear out that screen, and then now we're going to go stat, test down to option 6. Again, as I start typing in 450 over 3,000, 351 out of 1,800. And I want to choose less than P2, so that's the middle one. And then I go down to calculate. And again, it's only calculate once. Here, again, my overall P hat, PC hat was 0.166875. That's pretty darn close to what we have right here. Ours here rounded it to the third decimal. So that's pretty darn close. Our Z statistic was negative 4.04797. Again, what did we calculate it to be? We calculated it by hand to be negative 4.0468. Pretty darn close to what we have there. Remember, the calculator always gets it more exact. But we do have enough to make a decision. What's our P value? So what is our P? So on the, what is our P value? Our P value is 2.584 E negative 5. So that is 0.000025. And then 8. All right. Now we're ready to write our conclusion. 0.0000258. Sorry, my pen's being quirky. 258 is less than, it really doesn't matter what alpha we use. That is such a small p-value, it doesn't make a difference. It's going to be less than. Because remember, the typical ones we use is 0.01, 0.05, or 0.1. So we would be making the same decision no matter what we're doing. Since our p-value is less than our alpha, again, they didn't state an alpha in the problem, which means I got to use what? Technically, I use 0.05. We reject the null hypothesis. We do have convincing evidence that that a higher proportion of teens in 05-06 have hearing loss than teenagers in 88 to 94. Now, between the two studies, just some information here, Between the years 1988 to 1994 and the year 05-06, Apple introduced the iPod. If the result of the test are significantly significant, can we blame iPods for the increased hearing loss in teenagers? Are we allowed to say that? No, Kaida, you're shaking your head. No, why? Why no? We don't know if the iPods caused it. Okay, in order for us to say it was the iPods, in order to say there's a cause and effect, what do we really need to do? We need to do an experiment. We don't need to do a study. We don't need to do a survey. If we want to do cause and effect, we have to use an experiment. All right, and we got to test that is the iPod the reason behind it. So no, we can't. It's a coincidence that, hey, in between those two time frames, the iPod came out and the extra MP3 players came out, blah, blah, blah. But again, I was a teenager in 1988. That's about when the Walkman came out. You guys know what a Walkman was, right? All right, that was just your cassette player that you had on your hip and stuff. And then eventually we got like you really didn't have a portable CD player on your hip and stuff because it would skip. The laser beam wouldn't be able to do too good. So no, we need to run an experiment in order for us to say cause and effect. So I'm trying to write that in there. No, need to run an experiment for the cause and effect. If we're going to try to say that caused it, we got to do an experiment. is what we got to do. It just happens to be a coincidence. There could be other reasons behind that. We don't know, but so we got to do an experiment to make sure we, decrease some of the extra lurking variables that are out there that could cause the hearing loss. It may not just be the iPods is what's causing it. It could be other things. Okay, so that.